Hello, we have learned that both the fission of large nuclei and the fusion of small nuclei are nuclear reactions that result in the release of energy. In this video, we are going to look at specific nuclear reactions and see how we can determine whether the reaction results in the release or absorption of energy. Before that, let me give you an analogy. Suppose you have these two stacks of blocks and then you rearrange them into these two stacks. Do you see that overall, the total GPE of the blocks has decreased? So if you start from this and end with this, energy must have been lost by the system and released to the surrounding. On the other hand, if you started with these two stacks and ended up with these two stacks, you end up with a higher total GPE than before. This means that somebody must do work, right, to bring the system from this to this. This means that energy must be absorbed from the surrounding. So nuclear reaction is the same thing. It's just that instead of blocks, we are rearranging the nucleons. So depending on whether the nuclei are arranged in such a way that they are at a higher energy state or at a lower energy state, that will determine whether energy is released to the surrounding or absorbed from the surrounding. So take for example this one, which involves the bombardment of nitrogen gas by hydrogen-2 nuclei. So I'm assuming that the nitrogen-14 have negligible Ke, but the hydrogen-2 has quite a lot of Ke. So why must the hydrogen-2 be very energetic? Now remember, nuclei always repel one another. Because they are both positively charged, you need the hydrogen-2 to have a very large initial Ke so that the two nuclei can come close together, close enough for a nuclear reaction to take place. Okay, so how do we tell whether this reaction will release or absorb energy? Now let's assume that we are provided with the masses of all these nuclei. What we do then is to calculate the total mass before the reaction. So you take 2 point something plus this 14 point something, you get this number here. Do the same for the carbon-12 and the helium-4. Now look at these two numbers. You realize that the total mass has decreased. Since the total mass has decreased, we know that energy is released to the surrounding. Remember the mass-energy equivalence principle? The mass of a system represents the energy of the system. Why did the total mass drop? It must be because the system has lost energy, and the energy lost by the system has been released to the surrounding. If we were to do the calculation, then we say that the decrease in the rest mass energy of the nuclei must be equal to the increase in the Ke of the nuclei. The decrease in rest mass energy is simply the decrease in mass, this number here, the decrease in mass times c squared. And this should be equal to the Ke of the product nuclei minus the Ke of the reactant nuclei, which is just the Ke of the hydrogen-2 since I assume that the nitrogen-14 have negligible Ke. Meaning you start out with the Ke of the hydrogen-2, but after the nuclear reaction, the total Ke of the product nuclei is even higher than the Ke of the hydrogen-2. And the amount of increase is equal to the decrease in mass times c squared. Now sometimes we are provided with the binding energy of the nuclei instead. In that case, we just calculate the total binding energy before the reaction. So just add the 2.2 to the 104. So this is the total binding energy of these two nuclei. Do the same with these two numbers, you get the total binding energy after the reaction. Notice that the total binding energy has increased by about 13.6 mega electron volts. And an increase in total binding energy tells us that energy is released to the surrounding. Now there are many ways to remember why an increase in binding energy means a release of energy. One way is just to remember that binding energy is the mass defect times c squared. So if the total binding energy increased, it must mean that the total mass defect has increased, which means that the total mass is less now. And less mass means a release of energy. So that's one way. The second way is to see the binding energy as the energy that has already been cashed out. So as hydrogen-2 and nitrogen-14, I've already cashed out these amounts of energy. But as carbon-12 and helium-4, I cashed out even more energy. So the increase in binding energy represents the amounts that's cashed out during this reaction. Alright, so that's the second way to understand this. A third way to understand this is to see that if I want to break up the hydrogen-2 and nitrogen-14 into all its individual nucleons, that means all 16 nucleons, I need to put back 107 mega electron volts of energy. Get it? And now to put back all these individual nucleons to form carbon-12 and helium-4, 120 mega electron volts of energy will be released. Get it? I need to put in this much to unbind them, but they give me back this much when I bind them back. Of course, in reality, we don't have to break them up into individual nucleons and then reassemble them, yeah? But this is one way of imagining what's happening to help you remember why an increase in binding energy means a release of energy. So if you were to do the calculation, you say that the increase in total binding energy of the nuclei is equal to the increase in the Ke of the nuclei. And you may notice that we get the exact same answer as before. Alright, let's try this reaction. This is actually a very famous nuclear reaction. Historically, this is how we discovered the proton, by firing helium nuclei and a nitrogen gas. So again, I'm going to assume that nitrogen-14 carries negligible Ke, and it's the helium-4 that carries a lot of Ke that enables the two nuclei to come close together for the nuclear reaction to take place. Okay, suppose we are given the masses, so we can calculate the total mass before the reaction and the total mass after the reaction. This time you notice that there's an increase in total mass. An increase in total mass means that the system has gained energy. Where does it gain the energy from? From the surrounding. So we know that this nuclear reaction does not release energy. In fact, it's the opposite. Energy must be absorbed by the system in order for this reaction to occur. So who is providing this energy? It's provided by the Ke of the helium-4 nuclei. In fact, you can write the increase in rest mass energy of the nuclei to be equal to the decrease in the Ke of the nuclei. So the increase in mass, take the increase in mass times C squared, it should be equal to the initial total Ke, which is just the Ke of the helium-4, since I assume that the nitrogen-14 has negligible Ke, minus away the final total Ke, which is the Ke of the oxygen-17 and the hydrogen-1. Meaning after the reaction, the total Ke is less than before. Where has the Ke gone to? It has been absorbed by the system. Similarly, sometimes they provide us with the binding energy of the nuclei instead. In that case, just calculate the total binding energy before the reaction and the total binding energy after the reaction. You should know why this guy has zero binding energy, because it's the proton, yeah? It's already the basic nucleon. There's no mass defect, so it has no binding energy. So anyway, you notice that the total binding energy decreased. And the decrease in total binding energy means that energy is absorbed by the system. Less binding energy means less mass defect, yeah? Or you can see as less energy cashed out. Or you just imagine breaking this down into 18 nucleons and then reassembling them into the oxygen-17 and hydrogen-1. So when you unbind them, you got to supply 133 mega electron volt. But when they are bound together, they release 132 mega electron volt. So on the whole, we still must supply this amount. To do calculations, you write that the decrease in total binding energy is equal to the decrease in Ke of the nuclei. Sometimes they like to ask, what is the minimum Ke of this helium-4 in order for this nuclear reaction to occur? The answer is, it must be at least this amount plus the Ke of the product nuclei. It's not possible for these two nuclei to be at rest because before the reaction, we have the momentum of the helium-4. So the total momentum was not zero. So after the reaction, the total momentum also cannot be zero. So it's not possible for these two nuclei to be at rest. That's why the helium-4 cannot just supply this amount of energy. It needs to supply this amount plus the eventual Ke of the product nuclei after the reaction. Okay, that's all. Ta-ta!